Well, good afternoon, everybody, and welcome to the Carmichael Auditorium, the Museum of American History Bearing Center, for the 4th in our series of lectures on the transit of Venus, based around the exhibition Chasing Venus, which is the Smithsonian Library's exhibition on display in the first floor west wing of this museum. My name is Ron Brashear. I'm the head of special collections, curator of rare books at the Dibner Library of the History of Science and Technology in this museum, and the curator of the Chasing Venus exhibition. And I want at this time to thank the NASA Office of Space Science Outreach and Education Division for giving us funding to do this lecture series, which originally was planned to be 4 lectures, went up to 5, and now we have 6. So it's really going to be everything you wanted to know about the transit of Venus. And the transit of Venus is starting to infiltrate every aspect of the Smithsonian. Even the logo sometimes has been known to exhibit evidence of transit mania. Now, today our speaker is Dr. J. Pasachoff. He is the director of the Hopkins Observatory and a field memorial professor of astronomy at Williams College in Williamstown, Massachusetts. His academic credentials are exceptional. He's got his PhD from Harvard University in 1969 and has been at Williams College since 1972. Many of you may be familiar with J. Pasachoff through his works, especially his textbook, which title is Astronomy from the Earth to the Universe. It's now at least in its 6th edition, I think. I believe I remember having that as a textbook when I was teaching astronomy in college, not when I was taking astronomy, so I don't want to date him at that point. You may also have encountered the Peterson Field Guide series, a field guide to the stars and planets, which is also a product of Jay's authorship, and many other books, many other articles. His research interests are many. He has recently been studying with Professor R.J.M. Olson at Wheaton College on images of comets in art. He also studies the cosmic deuterium abundance, the primordial deuterium abundance, and its relation to cosmology. But his real big excitement, I think, is his specializing in studying the sun at solar eclipses. He's been at a huge number, I think at least 22, if not more, eclipses now. He's visited along with the students to study the sun and its corona and many other aspects of it, which I think explains his interest as well in transits of the sun by Mercury and Venus. One other thing I'd like to mention about Jay is he's been immortalized in the heavens now. There is an asteroid, 5100 Pasachoff, excuse me, which was named in 1993 by the discoverer Bowell. And that's something I think we all hope to have one day, but very few of us get our own asteroid, so congratulations to him on that honor. After the talk, if we have time for questions, we'll do that as well, and I'll talk a little bit more about the remaining lectures in the program. But right now, to talk to you about transits of Mercury and Venus, transits of Mercury and Venus, and the solution of the black drop mystery, J. Pasachoff.
Thank you very much, Ron. It's a great pleasure to be here with so many friends and friends and relations and general visitors. It's been very intriguing for me to get involved in this new problem. I don't know that it is yet in the Conan Doyle stories, but they just found this trove of Conan Doyle things that were going to be auctioned, and maybe there's something about the transit of Venus, and in them the timing is about right. In any case, as Ron points out, I've been very interested in eclipses for quite a long time, and though this is an eclipse of 0.001, a 0.1% eclipse of the sun, it falls sort of in that category and is related in some ultimate way. There are all kinds of transits of Venus, and here is, in fact, a transit of Venus. Venus going across the face of the sun in her chariot, from a wonderful book by Doppelmayr in 1742. Some of these books in the Smithsonian copies are on display here. The various images I'll show you now from the rare books are from my own collection. It's been fun to see Venus doing this. Of course, there are all kinds of transits of Venus here, and sometimes to find this on the sports page instead of the science page or the history page is a little unusual, but I've grown very interested in transits of Venus of all kinds in recent years. The transit of Venus actually has and had a very great importance in the history of the studies of the solar system, and indeed the universe, which was taken up by the solar system for centuries or millennia. And again, in Doppelmayr's book from 1742, we can see the traditional Aristotelian and Ptolemaic view of the universe with the Earth at the center, surrounded by earth, air, fire here, and water. Then the moon and Mercury, Venus, with the sun going around. But we all know that that's not the way it is. And in 1543, Nicholas Copernicus came out with his book, and things he'd been working on for some decades, showing that the sun instead of the Earth is at the center of the solar system. And so here's Old Sol, Mercury, Venus, and the Earth and Moon. In fact, we now tend to think that these are orbits, but they're not really orbits. Venus takes up the space between these two lines. And I've gotten particularly interested in this inner part of the solar system, the point being that only Mercury and Venus have orbits inside the Earth, so only Mercury and Venus can be projected on the sun. So the only two planets for which we can have transits are Mercury and Venus. People looked for a long time for the planet Vulcan, which turns out not to be there, and so there are no transits of Vulcan, indeed no Vulcan at all. Now, shortly after, in 1543, Copernicus came out with his ideas. Leonard Digges in England was writing about a whole variety of astronomical and other things. Here are the zodiacal constellations here in his book here by Leonard Digges here, solving all kinds of personal and universal problems. And again, he showed that the Earth was at the center, surrounded by the moon with the sun going around it. But 20 years later, his son Thomas learned of Copernicus's work and wrote a preface to the later editions of his father's book. And starting in 1576, and I have a 1596 copy that's shown here, in which he showed this perfect description of celestial orbs according to the ancient doctrine of the Pythagoreans, lately reissued or whatever by Copernicus. And here is the first Copernican diagram in English. And again, we see in the inner solar system, the sun here is covered by Mercury, surrounded by Mercury and Venus, and only those two planets can go in transit across the face of the sun. And so let us today talk about transits of Venus. Without knowing how far anything is in the solar system, nobody knew how big anything was. They could just look and see these points of light in the sky, and in fact in Digges's book they just had a picture showing the sun this size and Jupiter almost the same size, Earth and Mars about the same size, and Venus much smaller. And of course that is not what the latest NASA pictures show. And here's a series of spacecraft views of Mercury, Venus, Earth and Moon and Mars against the really giant sun. So to do that required finding out how far everything was away from everything else to know how big things are. And that came down to interpretation on the basis first of observations made by Tycho Brahe. And here is a diagram of Tycho's idea of how the solar system was arranged. He still had the Earth at the center, but then he had the sun going around the Earth, but everything else going around the sun. So he had a hybrid system, and he wanted to be remembered as a great theoretician. He might quite possibly be disappointed now to find out that we remember him as a great observer and we do not adopt his Tychonic model. We are still in the Copernican model that he was trying to supersede. He was joined in Prague by a young German astronomer, Johannes Kepler. Kepler had already been interested in how the solar system was arranged, and in 1596 he had the idea that there were the same number of Platonic solids as there are of planets, as they then knew of planets, and so there should be a one-to-one correspondence, and the things might be arranged in this beautiful set of things in which you see a tetrahedron and a cube and a dodecahedron, and the sun in the center of all this. And it's a wonderful idea and very beautiful. It makes a lovely plate, and you can see a diagram of it on the exhibit too. The only problem with it is that it's entirely wrong. But his heart was in the right place, and he set out to understand the solar system better. And he went to work for Tycho, and when Tycho died, without going into the details, the subject of another lecture, Kepler got Tycho's observations, and he worked on them and couldn't make sense in the straight Copernican theory with circular orbits around the sun. So, in fact, it took till 1609, but in 1609 he published his Astronomy Nova, from the motions of the star Mars from Tycho Brahe. He dedicated to the Royal Holy Roman Empire, Rudolph, and here his name is way down here in 1609. And in fact, we now sometimes say that Copernicus was not the first Copernican. It's really Kepler who was the first Copernican, because we now have a modern Copernican theory. And it really is based on Kepler's idea that the sun is the center of ellipses, and the planets orbit the sun in ellipses with the sun at one focus of the ellipse, and a second law that governs the speed at which the planets go around the sun. But what we want to go on with today is Kepler's third law. It took him another 10 years to find and publish the third law in a different book, his Harmonices Mundi, and the harmonies of the world. And in that third law, the square of a planet's period is proportional to the cube of its orbit's average size. So this set of proportionalities enable us to find out how far things were away in the solar system, because we could observe how long things took to go around and then calculate how far they were away. So we knew, for example, that Mars was 50% further away from the sun than the Earth is, and Venus was 70% of the Earth's distance from the sun. But we hadn't a clue as to what any of those distances actually were in whatever straightforward units we wanted to use. So Kepler, in any case, could predict where things would be in the sky, and he went on from using his first three laws to publish a book of tables, which he dedicated again to Rudolph. Here's Johannes Keplerus in 1627. And in his Rudolphine tables, they were not what we now call ephemerae. They were not transitory things. They didn't say June 1st, look at here, and June 2nd, the things will be that way. They were actually quite complicated tables. Here, in fact, we see Kepler working away down here, setting up this edifice that had been built on a pillar of Copernicus here, beautiful pillar, a pillar on Tycho, even more beautiful here. Going back to Ptolemy, was kind of an old-fashioned pillar, and the money raining down. You see the coins raining down here from the emperor here. So we do thank NASA for its support of this lecture series, and and the National Geographic Society for my forthcoming transit of Venus, and may that continue. In any case, Kepler's tables provided a way to calculate things, but they didn't give the actual positions of things themselves. And Kepler figured out there was going to be a transit of Mercury in 1631 and a transit of Venus also in 1631. But nobody could see the transit of Venus. It wasn't well situated, but they did see the transit of Mercury. It was a good check that Kepler was on the right track in doing his tables. And then Kepler had some family problems. His mother was being tried as a witch, and he had to travel to defend her. And on that arduous journey, he actually died and did not survive to the time of the second transit that, in any case, he had not predicted. And whether he would have predicted it himself or not, we will never know. But a young English astronomer, and by young we mean age 19 or 20, so that's pretty young, Jeremiah Horrocks did go back into Kepler's tables and use them to find out that there would be a transit that Kepler had missed in 1639. And he set out to observe that transit. He wrote his friend William Crabtree 20 miles away. One was in Muchhool near Liverpool. One was near Manchester. And in fact, this year on June 8th, in the anniversary of the observation of 1639, there is an international conference of astronomers being held, an international colloquium of the International Astronomical Union in Muchhool, and they will go to the exact place where Horrocks saw the transit, and I have declined to go to try to see an astronomical event for the middle of England, which does not seem to be the best chance of seeing it. We'll discuss my own observational plans later on. But we actually have sent a version of this talk as part of the meeting, they'll have there. So in any case, these pictures were drawn much later. Ira Crow drew this one, or painted this one in 1891, some 250 years or so after the actual event. So we don't really know what things look like, but we do know that he used a telescope to project an image of the sun on a screen. That's something we can do today with any little telescope, and you will see Venus crossing the screen. Well, here's a close-up of part of that. And there have been discussions, if you look back in some of the old British journal discussions of whether the rate of divergence of the rays in the picture are right and various technical aspects of the picture. But these pictures were both made years after, just a few years before that Ira Crow picture on the Manchester City Hall in England. They had Crabtree watching now, but the positions are all the same, and everything is the same in the image as the other image. They're just both made-up images. But in any case, those are the only two people who saw the eclipse, this 0.1% eclipse, the transit, I should say, in 1639. The device from 1639 is commemorated in a church window in Muchhool that has been there for a while, and just this year, because of the new transit that there's going to be, there's actually a new stained glass window in that church. So, after these pair of transits here, and the only one that was observed, we then look at the series of transits that was going to appear, and it turns out that transits come in pairs separated by 8 years, and then there's a gap of 105 years and a pair with 8 years, and a gap of 122 and a half years, and that then goes on indefinitely. And it really has to do with how often Venus and the Earth come around, and the fact that Venus's orbit is tilted to the Earth's orbit, and so they not only have to be in a line coming around, but they also have to be at the same altitude above the flat plane of the Earth's orbit. And so what happens really is that Venus goes across the bottom half of the sun, it goes across the top half of the sun 8 years later, and then it takes it another 120 years until it catches up at the bottom again. And I won't go into the technical aspects of it, but we do have these extraordinarily long separations, and I'm not really aware of another set of astronomical events that's predictable. It's not like a supernova that goes off randomly, but a predictable thing with this long time scale. There was the oddest event that happens even more rarely, so rare that we don't even see it again, is Mercury being hidden behind Venus itself, and those are both little tiny objects, and that actually happened once on May 17th, 1737. John Bevis, who did a wonderful star atlas, did observe that, and at that time what they were doing is just drawing the object. Here is the crescent Venus and a little symbol for Mercury there as they got closer together. And at that time they were timing things very accurately, and in fact we've been trying to set up some of our observations for this forthcoming transit of Venus by reading an old paper by Samuel Dunn, which is actually in the exhibit there, in which he goes on for pages and pages and describes minute by minute when Venus's atmosphere comes out and when things look a little closer. And so there's still something to learn from these 200-year-old articles. It was Edmund Halley of comet fame who figured out how to use the transit of Venus for scientific purposes, and he figured out a way of triangulating between the Earth and Venus. If you looked at Venus crossing the face of the sun, and you looked from different latitudes on Earth, you could figure out how close or how far Venus is to you. For example, if you hold, and I do this a lot, you hold your thumb up in front of your nose, a few inches away from your nose, and you close one eye and close your other eye. So everybody do that. Go ahead. Close one eye and then close the other eye, and you see your thumb seems to jump across the room. And now hold your thumb way out and do that, and you see your thumb moves much less. And so that's the effect they use. If you look from different places on the Earth and you watch Venus projected against the sun, does it move a little bit or a lot? And that tells you how far Venus is away. Halley worked out a way of doing it by timing how long Venus would take to cross the sun. Delisle soon thereafter improved in the method a little bit. But basically, when Venus went inside the sun, they would measure the instant that it went inside, and then it would go across. And you see that if it goes across the middle, it takes longer than if it goes across near the poles. It's just a shorter chord. And by getting many of those observations, Halley worked out a method of finding out the distance to Venus, and therefore the size of the solar system and of the universe, because Kepler's proportionalities then explain everything else, give you the distances to everything else. Now, this method that Halley worked out assumed that you could time to within a second or so, and our clocks were good to a second or so, when Venus would go inside the disk of the sun. And he explained this in several works. Here's some mention in one of his articles from the Philosophical Transactions of the Royal Society, and he was already talking about finding the Venus when it was in perigee, nearest to the Earth, and he had several articles related to this, and then the trick is then to do this triangulation, setting how far out in these orbits Venus is with respect to the Earth. So here's what the path of Venus would be in one of those old eclipses that were coming up, and the next ones to come up were in 1761 and 1769. Dozens of expeditions went all over the globe for those eclipses, and there's a lovely globe in the exhibit here with push pins in one color showing the 18th century transit observation locations on Earth, and another showing the 19th century locations. But when they actually made the observations, and the first of these was 1761, when Venus went inside the disk of the sun, it didn't do so cleanly. Some black region joined the disk of Venus to the sun, and as Venus went in for about a minute, the connection grew like taffy and pulled out and then eventually popped after about a minute. And that is known as the black drop effect. And it ruined their hopes of finding an accurate distance between the Earth and the sun, we know as the astronomical unit, because the timing was 50 times or so less accurate than had been thought. Observations were also made by Captain Cook. The British Admiralty gave a young lieutenant, James Cook, a ship and said, go to the South Pacific in order to observe the transit of Venus in Tahiti. And so James Cook took a ship, and the Endeavour, this very famous ship, and went out for the transit of Venus. And here's his actual journal on Saturday the 3rd of June. This day proved as favorable to our person as we could wish. Just to make it a little easier, I have a translation. And the air was perfectly clear, so that we had every advantage we could desire in observing the whole of the passage of planet Venus over the sun's disk. So we very distinctly saw an atmosphere all around the planet, and he said something and it turns out not to be the atmosphere. He was already wrong then, very much disturbed the times of the contacts, particularly the two internal ones. So that's the black drop effect, that they weren't able to get the time very well. Mr. Green was an astronomer from the Greenwich Observatory, came along on the ship to make these observations, and myself, we differ from one another in observing the times of the contacts much more than could be expected, and that's the black drop effect. So here's an image by Green. You see the whole atmosphere around Venus, but then when it even goes even further in, there's this black drop joining them. And here's Cook's observations, again with the black drop effect. So this effect has been around and talked around for several hundred years, 235 years, and we're talking about them now. Here is in fact a copy of the orders for acknowledgement from James Cook taking the bark Endeavour off to Tahiti. It turns out that they moved the Captain Cook's parents' house to Melbourne, Australia, where Naomi and I were able to see it last year. And then once Cook observed the transit of Venus very successfully in Tahiti, he then went meandering around the South Pacific and as spin-offs of astronomy, found New Zealand and mapped the east coast of Australia, just one of the many examples of how useful astronomical work can be and how it's worthy of everyone's support. The French astronomer, Guillaume Lejonty, was a major predictor of the circumstances of the transit, and he set out from France to see the transit in Pondicherry, India. His ship got to Pondicherry only to discover that it had been taken by the British during that war, and he wasn't able to board. He could see the transit from shipboard in clear skies, but at that time they had only pendulum clocks, as you know if you've read David Sobel's book Longitude, and so he couldn't get a good timing. His scientific purpose was not met, so he said that the next transit was only 8 years later, so he would stay. So he stayed around that part of the world. He went to Manila. He made some observations of various kinds, and he discovered he was going to be arrested in Manila, came back to Pondicherry to observe the transit in 1769. Beautiful, clear day. They're all set up already, and then just before the transit, it clouded up. So he was away for both transits. Finding out it had been clear finally in Manila didn't make him feel any better, nor did the ship that was shipwrecked on the way home, or the dysentery he got. And he got back after 14 years, discovered that he had been declared dead. His goods were being divided up by his heirs. His seat in the French Academy had been given away. And it is a spectacularly unsuccessful expedition, though he tried. I was glad ultimately to learn that he did, in fact, get his goods restored. They did make a new seat for him in the French Academy, and he did a few years later find a very lovely wife, and they had a couple of children, and he finally wound up living a long and happy life, dying finally just before he would have been beheaded by the Inquisition anyway. So maybe his timing wasn't so bad. But it's a wonderful story, and there are several books out on the transit of Venus that I can recommend to you that tell this story. My wife Naomi has especially recommended a wonderful novel from a few years ago, The Transit of Venus by Shirley Hazard, and I'll just point to you some of the astronomical parts, but of course there are many meanings to Venus and many meanings to a transit of Venus, and these are all, of course, played out in the novels and other plays of this title. Why did James Cook set sail in HMS Endeavour for undiscovered Australia, if not to observe en route at Tahiti the planet Venus as it crossed the face of the sun on the 3rd of June, 1769, and thus to determine the distance of Earth from sun? Tice, one of the astronomers, said the calculations were hopelessly out. Calculations by Venus often are. The other astronomers in the novel, Sefton Thrale, said there were distortions in the disk of Venus, a phenomenon of irradiation in the transit. We call it the black drop. The girl marveled. The years of preparation, and then from 1 hour to the next, all over. The young man explained that there were stages. He said there were the contacts and the culmination. They both blushed for the universe. There were extensive observations of the 19th century transits. Let's move up to the transits of 1874 and 1882, and all through Australia. Many wonderful observations were made of the atmosphere of Venus, as you see on the left, and the black drop extending itself, as you see on the right. And in fact, on this, and here's another just barely touching view here. And on display at the observatory, the old observatory in Sydney, they have one of the devices by the French astronomer Janssen, who made, in these early years of photography, a revolving device to take many images on the same photographic plate. He had these round plates The original plate, unfortunately, is not preserved, and what we have left is one plate that is actually quite possibly from a test rather than the actual transit, showing this first set of attempts to see Venus going in the face of the sun. We actually have photographs left over from 1882, and on display you can see one of the actual plates, or a box with several, but one is sticking out there, this plate that you see here on the right, and there are actually some plates. Well, there's a photograph, a print, it's still at Vassar College, other observations. So this is what we will all be able to see on June 8th. The Amherst astronomer, Professor Todd, went to the Lick Observatory in California, and recently those plates were located and put together into this animation here. A lovely animation put together by Tony Mish and William Sheehan. So, and then David Todd, actually, while he was out in California, his wife back in Amherst took up with Emily Dickinson's brother, was it, or his brother? And then when Todd came back, they lived in a menage a trois for a while. It's a very interesting story that I won't go. I'll leave that for personal research. But there's a long history behind those plates. I'll just deal with the black drop effect here, and you see even when the things were physically tangent, the actual view didn't allow you to determine the second of contact, to a second, the contact. So John Philip Sousa got very enthusiastic about the transit in 1882 and wrote that March, which is being played more this year than it has been for the last century, and then he actually wrote the worst novel I have ever read in my life, much later, and he wrote in 1920, it's largely about the personal relations on a ship that went to the Kerguelen Islands to view the transit back then, and there's just a little bit about Venus, and makes the point that if Venus made a daily, weekly, monthly, or yearly transit, it would not make much difference. But if a few years at most, you could wait to fix things. But it is wise to remember the next transit after the one we hope to view will not take place to the year 2004. And even in 1920, and even in 1960, and even in 1990, 2004 seemed impossibly off. And even on December 30th, 1999, we were waiting for the millennium, to see something in 2004 sounded quite far off. And it's incredible to realize that in just a few weeks, in less than a month, we will see a transit of Venus. So we are finally up to 2004. Now, I got involved more professionally in the transit a few years ago when I went to a meeting of the Historical Division of the American Astronomical Society, and I learned in a talk by Brad Schaefer, now at the University of Texas, that more than half of the references to the transit of Venus give an incorrect explanation for the black drop effect, claiming it's the atmosphere. And I invited Glenn Schneider, a colleague who works with the Hubble Space Telescope and has some very advanced image processing techniques, and Leon Golub built a telescope that is now in space on a spacecraft called the Transition Region and Coronal Explorer, a NASA spacecraft, and so we looked into this transit. And you can see here, there was a Mercury here, which is smaller than Venus, going across the face of the sun. You see, it's just a tiny little thing, and it was a grazing transit, but in 1999, Mercury went across the face of the sun, and the spacecraft studied it in great detail, and we're using that as an analog for what will happen for Venus. The Big Bear Solar Observatory, where I did my postdoc some years ago, had some observations of this transit, and the TRACE spacecraft looks all the time at the sun and was set to view the transit there. And if you look at the solar corona is actually a little bigger than the sun, so it wasn't quite as much as a graze. And then every once in a while some cosmic rays come in from space, making that kind of snow on the image. And so here's this coronal view of Venus going across the sun. And then if we look in continuous radiation, this is now in the ultraviolet, you can see Mercury doing this grazing transit. And then the next one is the white light, the visible light here, and you can see when it's just grazing here, it's not cleanly separated. And that's the black drop effect. There is a set of telescopes around the world that always view the sun in Learmonth, Australia, and if that gets cloudy, it can be picked up at Udaipur. Here's the accumulation here. And then when that sets or gets cloudy, then they go to the Canary Islands, to Altide. There are some excellent solar observatories in the Canary Islands, one in Tenerife, Altide, and one on La Palma. And here's a set of observations that I showed you from TRACE before, and you can look to see that the separation is not quite clean here. There's a black drop effect that lasts many, many seconds that prevents you from accurately measuring the transit of Mercury. Now, Mercury does not have an atmosphere, so it's not Mercury's atmosphere. And the spacecraft is above the Earth's atmosphere, so it's not the Earth's atmosphere, so there's no atmosphere involved in this black drop effect. And by analogy, for Venus, too, we expect to find the black drop effect largely independent of Venus's atmosphere, though the atmosphere will contribute in some way that has never been quantified, that we hope to look on in June 8th. Now, Len Schneider did his magic on various images, and we cleaned up the images in various technical ways to bring out the details in Mercury's image. And it turns out that it's significant that the sun gets darker near its edge. You see the sun darkening here? This is called the limb darkening. This is the sun's edge is the limb. And if we look in detail at the black drop effect here and make these equal intensity lines, the isophotes here, to the edge of the sun, you can see there's a big distortion near the edge of the sun. And by analyzing the details and the effect of how the sun gets dark near the limb, right at the limb, in the crucial place, it gets dark very abruptly. And that, plus the normal blurring that you expect from the finite size of any telescope, together account for the black drop effect. And no atmosphere is necessary or possible for this black drop effect on Mercury. And if we take out both those effects, you see we're left with a perfectly round image. We've taken account of all the other effects. And so we've been working on this for some time, and we just had an article about that appeared in the journal Icarus in the last few months, and we hope to do this kind of observation in detail for the forthcoming transit of Venus with a variety of spacecraft and telescopes on the ground. The best solar telescope now that exists is the new Swedish solar telescope on La Palma in the Canary Islands. They actually have a way of distorting the mirror in 37 different places in fractions of a second to take out the effect of the Earth's atmosphere and get these very steady images. So here is a view from the new Swedish solar telescope. Here you can see some limb darkening, and there's no black drop quite here, and we'll see what all those effects are when we view the transit of Venus soon using that. Now, there was a transit of Mercury in 2003, which we did observe with TRACE. But in order to make this nice movie going all the way across, they did some compression of the data coming down all through. And so though we have the whole movie, and because TRACE is in an orbit around the Earth going around, the position varies, so you could actually find the distance to Mercury in this way from studying the wobble. But they didn't have detailed enough data, uncompressed data from the black drop, so we were unable to do our same kind of observations, and we hope we have headed off any possibility of doing that same kind of compression for Venus. So it was very useful to prepare for the transits of Venus by looking at the transits of Mercury. Here's the white light image from TRACE looking at this last transit of Mercury in 2003, in which they did various parts. You can see the limb darkening there, for example, as Mercury travels across the face of the sun. Venus is bigger and it's closer to Earth, so it will actually look 5 times bigger than Mercury in projection against the sun. And so here we are, up to 2004. Fred Espenak of the Goddard Space Flight Center makes detailed predictions, and we know very accurately the times that will occur, and we're all set up to observe. There are major educational projects in the United States from NASA and even more in Europe, all through Europe, by the European Southern Observatory to coordinate school children all across Europe to make observations of these timings and put them together and make a big measurement of the distance of Venus from the Earth and therefore the Sun from the Earth in that way. It turns out that the whole transit will be visible from Europe and Asia during that time. You see the peak is actually from Saudi Arabia, and there will be good observing in Iran and Iraq and a couple of other places where I don't plan to go for those observations. But nonetheless, one can do better than observing from here, unless this is where you happen to be, because the transit will be mostly over by the time it hits the United States. But in the eastern half of the United States, people low in the east at sunrise will be able to see the end of the transit and one of the black drop effects, the final black drop effect. In 2012, again from the continental United States, then there will be the transit will be in progress when it sets, and we'll see the first but not the second black drop effect, though Hawaii should be a good place to observe then, and again eastern Australia or Alaska for that matter, for the transit of 2012. Before that, there will be a transit of Mercury visible from the United States, partly visible from the United States in 2006, another thing that we can look forward to. But the main event is to see the transit on June 8th. There is not a single person alive who saw the last transit of Venus. I do follow in the Guinness Book of World Records who the oldest person in the world is, and in the newspaper you often see when somebody dies, the last person to die recently was 115, the oldest person in the world. The next person was 114, and so nobody on Earth has seen a transit of Venus, and we have a chance in a couple of weeks to see one, and in another 8 years, I hope, to see a second. I was very glad that the Committee for Research and Exploration of the National Geographic Society has sponsored an expedition that we're taking from Williams College to see this transit, to see both black drops. So we wanted to go somewhere in that white zone where we could see both black drops. We got some additional support from Sigma Xi, and we've set up a website at transitofvenus.info that has a lot of maps and other things, and a link to this exhibit and various other interesting things. Now we can see how things will look from the spacecraft because we will be using the TRACE spacecraft, and because of the different locations on the Earth, Venus will appear to go up and down a bit on the face of the Sun. And from that triangulation, we should be able to find the distance very accurately to Venus. From the Earth itself, we don't see that wiggle, and we see that Venus will go across part of the Sun there, and we hope to watch the whole phenomenon, including the atmosphere and including the 2 black drops. Now, 5 hours after there's a transit of Venus as seen from the Earth, there's a transit of Venus as seen from the Moon, and in fact, my colleague Glenn Schneider has arranged for a telescope in Arizona to watch the Moon all this time. They can't see the transit directly, but they will watch the total brightness of the Moon to see if it dips by a little bit, and they'll actually be doing it spectroscopically. They'll use a spectrograph to see if the spectrum changes a little bit. And I will be using a spacecraft that measures what's called the solar constant, the total energy coming from the Sun. It's called AcromSat, and we expect to be easily able to determine the drop in brightness by about 0.1% as Venus goes in front of the Sun. This is particularly interesting because in the last 10 years, some 120 planets have been found to be in orbit around other stars. Some small number of those actually have planets that go in front of the star, causing a transit. At the moment, 2 weeks ago the number was 2, and last week 2 more were discovered, doubling the number of those. We now know of 4, but we confidently expect to find dozens or hundreds of these in the next few years. And as we're able to observe them in more detail, we would like to have detailed observations of what a transit looks like close up, and we can see that in the transit of Venus. So we're trying to arrange a variety of kinds of data to be recorded on June 8th that will be useful for comparison with these exoplanet transits, the transits of these extrasolar planets around other stars. So the transit of Venus is not only a historical event, but also one with a hope for the future and an interaction to some very interesting future observations that will be made. Here's the view from the Moon Center, and again, Venus will block 0.1% of the light and perhaps affect the spectrum in some way we can determine. If we were on the Sun, looking back at Venus going across the sky, Venus is closer to the Sun, so it would just entirely block out the Moon. And here is the view from the Sun looking at the Earth with Venus drawing across. And you see how this spacecraft that we're using, the TRACE spacecraft that we'll observe, goes around in a polar orbit around, always keeping the Sun in view. So here's the map again, a different map in particular, but here's the zone in which the whole transit will be available, and I will be in Greece at that time, and we will have with me my colleague Bryce Babcock. Glenn Schneider will come. Steve Sousa is working in Williamstown, and we will have some Williams College students with us: David Buss, Joe Gangestad, Alan Cordova, Owen Westbrook, and an exchange student, Kayla Gaydosh, an alumnus who's now a grad student. And we're working in particular with John Sirodakis at the University of Thessaloniki, I learned yesterday as a pronunciation, who will provide us with some telescopes from their university there, and we're bringing the electronic devices. And the transit will be partly visible from here, and you can see the zones of how long after sunrise it will take for the black drop to appear and Venus to leave the Sun. So somewhere around an hour and a half after sunrise, so low in the east is when from here you will be able to see the transit of Venus. So you'd better see that one. If not, you'll get another chance in 2012 to see part of a transit, and after that you'll have to wait till December 11th, 2117, or December 8th, 2125. So I think the odds favor trying to see these transits in 2004 and 2012. In closing, we have this very nice historic image from Vassar College from the famous professor Maria Mitchell, who, when she was a girl in Nantucket, discovered a comet and won the King of Denmark's gold medal for that purpose, went on to be a major American professor. And she and her students took this image in 1882, and this is more or less what we will see on June 8th, in a few weeks. We have worked on the Canary Islands image a bit to get rid of some of the jogging and the guiding that was there. I am going next week with 2 of my students, David Butts and Joe Gangestad, to the Canary Islands to use this telescope, and then we're studying in particular not the transit, though people will be getting ready a little bit, but we're studying the very fine detail on the edge of the Sun and linking that with the TRACE spacecraft. But people are also preparing to observe the transit of Venus from that spacecraft, and also potentially spectrographically, in addition to just the images. So here's the transit of Mercury, and here are some simulations of the black drop if the resolution caused by the effects of blurring of the air and the telescope are to a certain extent. You do tend to see this black drop, so we'll be analyzing that. And here is again an actual observation of the transit of Mercury, this last transit of Mercury, as seen from the Swedish Solar Telescope, and now, in closing, an image of what they expect to see in a couple of weeks from the transit of Venus. And I hope we all get to see it very clearly. Thank you very much, Ron, for inviting me. Thank you all for coming. And I'm glad to answer any questions. Yes?
These are all in visible light, but in H alpha, you're going to get as much of the black drop as looking at it. And will the fact that you're looking
the question is, what happens at H alpha? H alpha is a kind of radiation from hydrogen, and there's a lot of hydrogen on the sun. The sun is 90% hydrogen, and in fact, the image in H alpha is a little bigger than the image in this continuous, regular, ordinary light. And so when you are actually at the edge of the visible sun, there still will be some H alpha beyond it. So we've been discussing a lot what it would look like in H alpha. Nobody has actually observed in H alpha, though there are some spectra in H alpha, actually, from 1882. And the latest idea is we won't see the black drop at that time. You may see a black drop a little later at the edge of the chromosphere, but that's an uneven edge, which is in fact what my Canary Island observations next week are going to be. So it'll be different. Also, one of the spacecraft, the TRACE will see it next week, one of the spacecraft that's a very good solar spacecraft is called SOHO, Solar and Heliospheric Observatory. It's actually out 1 million miles towards the sun from here, so it will not have a transit that will go across the disk, but the transit will go across, so the solar corona will have the silhouette of Venus against it, so it'll be a transit of the corona. So those are interesting things to see, and they'll be nice pictures, but can't be used for this solar system scale. Yes?
How about when you're dealing with shadows cast by the sun or a light bulb, such as bringing your fingers together?
Yes.
You get the same effect?
Well, that's related to this point spread function. That's the inherent blurring. If you bring your fingers very close together and you look, they do seem to blur together as you're pointing out. And so that's one of the two things. But that amount, if you evaluate it quantitatively, does not completely account for the black drop we saw from Mercury. You do have to add in the effect of the limb darkening too to make it whole. And so what we're trying to do is quantify all this and see what all the effects are. Yes?
I'm going to be in the middle of China during this. What about the time? Soviet age?
Well, I can give you the time in universal time. Now, do you know how many time zones there are in the United States? Well, there are 4 in the continental United States, not counting Hawaii and Alaska and Guam. Do you know how many there are in the Soviet Union? Something like 11 or 12 in the Soviet Union. Do you know how many there are in China? 1. So that is an example of centralization for you. And the farmers in one part of China have to get up very early. So in fact, we could look up how many hours of time difference it is from China to UT. These times are given in really British Central Time, Universal Time. And so it actually happens in the same time universally, and then it's just a question of the number of hours for your time zone. We can check that. Yes, so I can give you the times in Universal Time, and then you can figure that out. But you should see, well, you see, it's in the afternoon there, clearly, because in this part of China, if you're in Shanghai, I don't know where you'll be in China, it'll be near sunset, so it'll be in the afternoon. Yes?
How is the new Swedish telescope advanced technologically?
This is Mr. Butts, who's the father of my student who's coming with me on this, so it's a fair question from many points of view. The Swedish Solar Telescope was very advanced in a technique called adaptive optics that people have been developing in astronomy for the last 10 years, in which the mirror or one of the mirrors in the system is distorted to take out the effect of the Earth's atmosphere. A couple of years ago, they rebuilt this telescope from scratch. They put in a bigger mirror that's actually a full meter, bigger than a yard across. and there are actually 37 actuators, so there's quite a lot of control, and the images that it gives are just spectacular. So it's a telescope that was specially made and rebuilt with all this in, and telescopes all around the world are being refitted with this adaptive optics, and here it's designed in from the beginning. The other solar telescopes are getting this stuff. No, he's not involved in the ground-based observing. He's busy now building a spacecraft called Solar B to be launched by the Japanese, which will have a telescope in space that will give these images that will be launched in about 3 years. And so we will continue to work with him on that. He's not specifically involved with this telescope. Yes?
Since the atmosphere is often brought up, I'm asking you to address that issue.
Venus's atmosphere?
Yes.
Yes.
And thinking, and you might have suggested, you might have read recently, is that the atmosphere not only is visible beyond the limb of the sun, but somewhat internally. Is that possible in the brightness of the sun?
No. I'm not familiar with the reference you're making, but sometimes there are film effects when things blur over just because of the contrast between dark and light. Even to just put it up in PowerPoint, this image is less good than a photographic image, and you can have what are called irradiation effects, which people have invoked. Something bright outside, something dark, you get a little blurring over the edge, but those are not real effects, and you have to take account of those effects. Those are just artifacts.
Only beyond the limb of the sun will that halo that
Well, I thought you were talking about not on Venus's disk, but whether you can actually see Venus after it moves onto the disk a bit, we do have old drawings that show that it should be visible. So we'll try to take pictures of all kinds, and it looks as though, from some of these old images, that it should be visible on the disk a bit. A couple more questions. I see Ron moving. Yes?
Venus occurred regularly in 1960, and the Naval Observatory in 2016 passed with the 2016 telescope, but they were unable to see regularly since it was before the Venus culminated. However, at 2 o'clock or so in the afternoon, one of our passive special observers observed both Venus and Regulus on the capture circle after Venus had stopped and out of the way in front of Regulus. And I saw a Venus occasionally is occulted by the moon, just like stars. And I saw one of those at 5:30 in the morning. It hit the thing. So Venus can be some rather unusual other things that is attached to Venus.
Thank you very much. There are these very interesting other transits you point out. Come say hello afterwards so I can talk to you a little bit, please. And the Naval Observatory has been very active with you personally. There are other kinds of events that are related to eclipses and transits, including occultations, and I think I'm not going to be allowed to give another lecture, but I have PowerPoint here for a lecture on occultations of a star by Pluto, in which we're studying Pluto's atmosphere by exactly the way that you were using to study Venus' atmosphere, and it's wonderful to see these things go in front of something else when the weather is clear. And I wish you all clear weather and happy observing on June 8th and for all your other astronomical events. Thank you.
Well, thanks again to Jay for his marvelous talk. And before you go, I just want to remind everybody to be here 2 weeks from noon today on June the 3rd, when David Dvorkin, curator at the Air and Space Museum, will talk on public reaction to the transit of Venus in 1882. And at noon on Monday, June 7th, Michael Chauvin will give a talk on the British expedition in 1874 to Hawaii. And then on June 8th, we'll have clear weather, and you'll all be up at sunrise to see the transit of Venus, I'm sure. So if you haven't had a chance to see our exhibition yet, please do so. It's over in the first floor west wing of this museum. It'll be up through April the 3rd, 2005. So you got plenty of time to see it, and thanks again for coming, and hope to see you in a couple of weeks. Bye-bye.